So we left off last time talking about the logistic model, and we were talking about how there's two forms of the logistic regression model. There's the form over here, the probability form of the model. The probability of y given some x's is this thing, 1 over 1 plus e to the minus alpha plus beta 1, x1, x2, and so forth. So this is one format of the model. And then we showed that if you take the logit of this thing, which is p over 1 minus p, and then you take the log, you get this much more familiar, friendly, nice version of the model down here. So this is the logit or the log odds form of the model. And so we wanted to talk about just what this looks like in a real situation. So here is that MRSA example again. And here's one model. You can make a whole lot of models, even given the several variables that we introduced. But here's one model. It looks at the probability of having resistant staph infection given these four variables: hospitalization, age, sex, and previous antibiotic use. And it considers just kind of the single factors one at a time in the model like this. There's no product or interaction terms, nothing fancy, just a single term for each model. Alpha, beta 1 times previous hospitalization, yes, no. Beta 2 times age, beta 3 times sex. So this is not using x's here. We're actually just putting the name of the variable in, but it's kind of representing the idea that, like, if previous hospitalization is 1, a 1 goes here, or a 0 goes here. We're using just English because English is a little preferable to Greek where possible. And so in biostatistics courses, you may not see the variable name just kind of thrown in here, but that's just our way to make this a little friendlier. And of course, our friendly faces. So this is one model, right? You can just have the four kind of main effects over here, one for each term. And so you can say, okay, that here's our model. Let's say I have someone who's hospitalized, age 35, sex 1 is male, and then they have previous antimicrobial use, yes. Right, you can say, okay, well, what's their probability of, having resistant infection? And you would put those values into here, and you would kind of turn your crank on your calculator or whatever, or a SAS, as it's going to be the case. And what you would predict from your model, given these covariates, you would get a predicted probability of having resistant infection. So that's one thing you might want to know. But then we also talked about this other stuff that you might want to know is more general than just like, give me the probability for this person. You might say something like, what's the odds ratio for previous hospitalization once we control for all the other stuff in the model? And that's, as I'm sure you've seen so far in your epi career, this is a very, perhaps the more common thing you want to know, is this general kind of ideologic conclusion about some situation. In this case, in your data, in this case, it's this association between hospitalization and resistance. And so we said that the odds ratio is e to the beta 1. And beta 1 is the coefficient corresponding to previous hospitalization. Okay, so why is that? And I think this has been, you know this, we've seen this in lab already. Well, the reason for that is the following. If this was the probability form of your model, 1 over 1 plus e to the minus all this, we said that the odds is e to the alpha plus beta 1, so forth here. I'm plugging in hospitalization here as value 1. You'll see why. But this is the odds version of the model. Under hospitalization equals yes, which is why I have a 1 here. And the odds of the outcome given hospitalization equals no is this thing right here, but with a 0 instead of a 1 for previous hospitalization. So I made two jumps kind of between here and here. This is the probability form of the model. This is the odds form of the model, not the log odds form. The log odds is just what's in the numerator, right? That was the logit, the log odds form. E to that is the odds form, right? E and log are kind of, they're the anti-functions of one another. They kind of undo each other. And so this is the odds form of the model. And by the way, I'm specifying ahead of time that this person, or this this represents the odds when someone is previously hospitalized, because there's a 1 here. I don't care what age is. I don't care what sex is. These are going to take on any value. I don't care right now. I'm saying I just want to know, how do I write the model when you're previously hospitalized? When you're not previously hospitalized, it looks like this. It's the same model again, but it's a 0 here. Everything else is the same. I'm going to I'm blind to it right now. I don't care. I just want to say, what's the model like under these 2 scenarios? And so it turns out, what's the ratio of 2 odds? Well, that's an odds ratio. So here we are. OR equals that, right? This is the ratio of 2 odds. And lo and behold, a lot of stuff is going to start to cancel out. Another way to write this big fraction here, this e to the alpha plus beta 1 and so forth over this denominator, when the ratio of e to the x over e to the x is you start subtracting. And I know this might be digging back to a part of your brain that you may not want to dig to, but this is one of the things with taking ratios of exponentials is you can subtract them. And so this becomes e to the numerator. This is the numerator piece minus the denominator piece. And when you start subtracting, now things start to cancel out, right? So the alpha minus alpha, that goes away. Beta 2 times age minus, this distributes up, minus beta 2 times age, that goes away. Everything cancels out when you subtract in this numerator piece, and not the numerator, up in the exponent here. So everything starts to subtract out, except you have beta 1 times 1, and there's no corresponding piece because it was beta 1 times 0. This was a 0, so this went away. So what you're left is, after you start canceling everything out, what you're left with is just beta 1 in the numerator. Beta 1 times 1. That was it. Everything else conveniently goes away. So in the no interaction model, this is a no interaction model, the odds ratio is just e to the beta 1. Everything else conveniently goes away. So what's really great about this is we did not have to specify what all these other values were. This is true for any age, any sex, any previous antimicrobial use, any values of these covariates. It doesn't matter, they all go away. This is not going to always be the case, and as we'll see in some other situations, but in this simple situation, everything conveniently cancels out. That's really nice. So that's why it's e to the beta 1. So again, in our specific example, here was our model in the probability form. Here's the logit version, and the odds ratio is e to the beta 1. And if so what is this? This is nice to see in PowerPoint, but if I actually had a data set, what would this look like? If I actually ran proc logistic, well, what you get, if you did model, actually do I have the commands in here? I don't have the commands, but in, proc logistic, we have model, the outcome equals, you'd have previous hospitalization, age, sex, PAMU on the right side of the equal sign. And what you get is a table like this out of SAS. And what it's going to say here is intercept, previous hospitalization, age, sex, PAMU. Okay, what are these things that say estimate? Well, these are the estimates of these coefficients in your model. So this is the estimate of the intercept, alpha. Here's beta hat 1, previous hospitalization, that's this, age, sex, PAMU. So using this value of the estimated coefficient, you can just say, okay, well, I can exponentiate 1.4855, and that is the odds ratio. So SAS actually gives you also a second table of odds ratios over here, and all it's doing is hitting the E button for you. So, which means that if you are doing a more complicated odds ratio, which we're going to do using the contrast or the estimate statements, don't use this table. This is not very helpful if you're trying to do anything fancier than just e to the beta. This is just the e to the beta table. It may not actually be an odds ratio that's meaningful or useful to you in your life. So many times we're going to have to do something else. But in the simple e to the beta way, this is a table of e to the betas, and that's how you get from 1.4855 to 4.417. Okay, so this is what SAS is going to give you at representing all of this, and it's not going to call it beta 1, 2, 3, 4. That's our nomenclature. It's going to phrase things in terms of the variable that that the coefficient is associated with, like previous hospitalization, age, sex, and PAMU. Okay, and notice these are kind of 1 degree of freedom, meaning there's just one parameter associated with each of these, essentially. Okay, so here is just what we saw out of the logistic model. This is the odds ratio. In this model, we estimate the odds ratio for previous hospitalization is 4.417. So it looks like this is, 4.4-fold the odds of having resistance when you were previously hospitalized. And if you compare that to, if you compare that to what you got from the stratified analysis, it's a little different, actually. And you get, when we stratified on 3 factors at a time, age, sex, PAMU, we got 4.66. So not exactly the same. Not exactly the same. So does anyone have some, why is that? You want to guess? In front of 150 of your peers? Okay, I'm going to throw out several reasons. So one reason is age was considered continuous in our model. But here, remember I said one of the drawbacks of the Mantel-Hansel, the stratified stuff, is you had to categorize age. So one thing here, I forgot exactly how many categories. I think it was just binary, I think is the way we did it originally in the stratified analysis. This is just 2 levels of age. So age is considered differently. So that's going to be some source of discrepancy rather than a continuous age. And then the other piece is that this was kind of stratified with kind of almost interaction terms. It was stratified into 8 tables of all combinations of age, sex, and PAMU. We have no interaction terms in this model, and so it's a little hard to explain without going into the interaction terms, which is what we're going to do next. But basically, this is kind of this is as if we fit a model with all interaction terms for these pieces in some sense, perhaps. So they're not going to be exactly the same, but it's actually pretty close. So that's actually like comforting when you do things 2 different ways and they're rather close. And what does it mean when the odds ratio, if this is continuous age, what does this odds ratio of 1.036 mean? If this is a continuous variable? Yes, 1 unit increase. This would be the increased odds, for every year age you go up. So if you're 30 versus 31 or whatever, if you're every 35, 36, and so forth, every year multiplies your risk in some sense by only this little amount, but it accrues. So this is you have another 3.6% change in your odds for every year older you get. So over 10 years, 20 years change in age, this would be a much bigger number. And so this is for a 1 unit change, which is why it's so small. We can manipulate how SAS reports this, by the way. There's a command, there's the odds ratio command, and there's something called units. There's the units statement in Proc Logistic, and you can actually tell it, hey, actually, though my data is at 1 year age increments, I actually want to see the result of the odds ratio in 10-year increments, or reflecting a 10-year change in age, let's say. And that's using the units statement. We can also, we're going to talk about the contrast and estimate statements. Those can be used to specify the number of the units as well. So, but that's why this looks kind of small and not interesting, but that's really because it's a 1 year change. Notice it has a confidence interval that's above 1. This is a significant increase. It's just small because it's 1 year. So, what does this comparison look like? What if I fit a really simple model? So, what if I just fit this model? logit P of X is alpha plus beta 1 times previous hospitalization, so not really controlling for anything else, just previous hospitalization. The odds ratio is e to the beta. And I get, this is my estimate, 2.46, which needs to be exponentiated. And then I get 11.673. Now it actually matches the 2x2 table kind of approach exactly. And that's because we don't have these issues of, well, we dichotomized a continuous variable, or we kind of ignored interactions in some way. So this is exactly the same. 11.67 is 11.67. So you can now, you can forevermore can get your odds ratios at a proc logistic, your simple odds ratios at a proc logistic instead of not survey freak, regular proc freak. If you ever wanted to do that. Or you can just keep using proc freak, but the answers are the same. So that's good. That should bring you comfort. And so, so we just kind of demonstrated the odds ratio in this simplistic model where there's nothing fancy going on. We have a dichotomous exposure, previous hospitalization, and we have no interaction terms or product terms. But it can get more complicated. And so the more formal definition of how you find an odds ratio out of a logistic model looks something like this. The idea is that you're comparing two kind of profiles, two types, groups of people with different values of their covariates. And that could be you can specify any comparison of a person with covariates X star, X1 star, X2, their age is this, their previous hospitalization is that, and so forth. And you're comparing them to another profile of person. And you're just taking the ratio of those odds. So you're saying e to the alpha plus beta 1 times X1 star, beta 2, X2 star. So in the previous example, we held a lot of these constant and things canceled out, but they don't have to. You can generally always put whatever you want here in these, for these X's and the X stars and so forth. And when you take this ratio, you get kind of what we saw before, is that you're subtracting the denominator's values here from the numerator up in this coefficient, alpha plus beta 1 X1 star and so forth. But what's cool is you can actually group these pieces in some way. So no matter what X star and X are and all of that, the alphas always cancel out. Okay, so that's going to be good. So you're going to get alpha minus alpha. That's going to be nice. And then what you get is beta 1 times X star 1 minus X1. Well, how did that happen? I kind of factored out, in this here, I factored out beta 1 times X1 star, and then there's X1. See, I factored out the beta 1 that was multiplying X star 1 and X1. So you keep doing this, and what you get is you can factor out every single pair where it's the same X1 and X star 1 and beta 1 and so forth. You can do this all the way for all your coefficients. And then you can write this even more generally as this formula. E to the sum of each beta times the difference in the coefficients associated with that beta. Okay, so what does that mean? Well, in our previous situation where everything was the same except for exposure, age was the same, sex was the same, we were holding those constant, they're the same. Well, it's sex minus sex, age minus age, and so forth. Everything will cancel out because it's this thing minus itself. Except for the exposure. That was the only one where it was 1 minus 0. And that's how you get to e to the beta 1. So this formula simplifies all of this business and figuring out what cancels and taking the ratio, looking at what cancels and so forth. This just says actually it's just e to the beta and then the sum of these betas and just look at the ones where they're not the same. And that will give you a general kind of odds ratio expression. So, this basically just rewrites, here we go. This is rewriting the example that we had earlier with this formula. So when we had just previous hospitalization as the only thing changing, age cancels out, sex cancels out, PAMU cancels out, and then we were left with just e to the beta 1. Okay, so This looks like a whole lot of work to just get back to e to the beta, but we didn't have to just vary. We could have said, what was the odds ratio comparing a hospitalized female to a non-hospitalized male? I'm not sure why you want to know that, but there might be a situation to specifically compare two profiles of people in some way. What if you have some referent group and you're looking at the non-hospitalized females and you want to compare everyone else to them? Well, in that case, you'd be varying sex as well. So sex would be 1 versus 0, let's say. And now it would be e to the beta 1 plus the beta associated with sex, beta 3, parentheses 1 minus 0. Because the sex, male and female, there's two values, the values are different. It's male and female. And now the odds ratio in that situation would be e to the beta 1 and plus beta 3. So depending on how fancy you want to get and what your needs are, this is going to get more complicated than e to the beta 1. And the way to guide you through that complication is this formula. And you don't have to deal with all these intermediary pieces. So it's the sum of betas times where the difference in the x's associated with those. And this lets you zoom in and say, okay, what's changing? Okay, previous hospitalization is changing, sex is changing. Throw the rest away. I'm just going to focus on those two in my odds ratio. That's the beauty of this formula. Oh, here it is. Look at that. I just said that. So, okay, so here's a situation where we have previous hospitalized and sex 1 versus not hospitalized sex 0, so male to female. This odds ratio, I know the slides, they were just somewhere in the back of my head and I got ahead of myself. So here's that situation that I just described where you have the beta 1 and the beta 3 star in the odds ratio expression, and it's 1 minus 0 and 1 minus 0. And here you get that the odds ratio for this specific comparison is 11.2. Okay, so this is where we're diverging from e to the beta. And by the way, this is kind of a multiplicative thing, right? So if this is the formula, e to the beta times 1 plus, so e to the beta 1 times 1 effectively plus beta 3 times 1. It's also true that this expression equals e to the beta 1 times e to the beta 3, which is what I'm saying here. So when you see when this plus can be converted into a multiplication. So what this means here that e to the beta 1 plus beta 3 is equal to this. If you multiply, this is just e to the beta 1 and this is just e to the beta 3. You get the odds ratio. This on its own is the odds ratio for previous hospitalization, and this is the odds ratio for male versus female. This is just each e to the beta separately. This product is exactly the same. Okay, so if I didn't have to add them first, I actually could have I could have gotten just the odds ratio for previous hospitalized, just the odds ratio for sex 1 versus 0, multiply it together, and you get 11.2. So what does that mean? It means that these are kind of multiplicatively changing the odds. So this is the formula that kind of captures that. So another way to think of the odds ratio in a no interaction model is, okay, you're previously hospitalized, great. Your odds ratio is 4.42. Yeah, that's your odds ratio. Okay, oh, you're male, multiply it again by 2.54. And so it could have been, oh, you're female, so it could have gone down. It could have lowered your odds. It could have been, oh, you're female, that would be 1 over 2.54. So basically, it's almost like you're independently multiplying through each of these effects. Okay, this is where, like, thinking back to other epi courses, we talk about multiplicative versus additive ideas and effects. The logistic model is a multiplicative model. Every term kind of multiplies the risk. It's a multiplicative factor. In linear regression, you're adding. It's an additive model. Every factor adds to, let's say let's say the outcome is blood pressure. This term adds or subtracts from the blood pressure, the mean blood pressure. In the logistic model, this is all multiplicative. It's saying, okay, you're hospitalized, we multiply your odds by 4.42. You're male, we multiply it by 2.54. Multiplicative model. That's all I'm saying. So, but it's a different kind of way of thinking than additive. Additive is maybe like a little more intuitive, maybe. But we're in ratio world here, and in ratios, we're kind of multiplying by these up and down factors. Twofold the risk, half the risk, so forth. And so these all kind of independently come together. So just something to keep, this is just something to keep in mind, that this is really how all the features of the logistic model work. And so, by the way, you could write, if you like Greek symbols, you could rewrite your e to the sum of these betas times their x times the difference in the x's, the previous expression. You can actually rewrite it as the product. This is the product of all the e to the betas. Okay, that's exactly what we just did here. We're saying instead of adding first, we can just do them individually and multiply them. So that's another way to think of this. So everything gets a little more complicated with interaction terms. Okay, and we're going to see in the EVW model that we are going to embrace interaction terms. So what is this about? Here we have a different model where we have previous hospitalization, we have age as just terms by themselves. And then we have this other thing, previous hospitalization times age. And so what we're allowing here is the risk to change based on the product of these two. It's not like, oh, you're this age and you're hospitalized, this is always your risk, as the sum of these two pieces. We're now saying that the effect of hospitalization itself is changing across values of age, or this is, you might call this effect modification, right? Which we're going to formalize in the EVW model as an effect modifier. So this is saying this is allowing the previous hospitalization effect to change across age. And so the odds ratio expression is still the same idea in some sense, in that you're comparing kind of a numerator versus denominator person. So let's say you wanted to know in this model, what's the effect of previous hospitalization, the exposure. What is the effect of the exposure? Okay, so you can define one person, your X star person, is someone with a 1 for previous hospitalization. Age is whatever. We're going to keep it generic. These are the same age. It could be 17. They're both 17. It could be 22, whatever it is. And then we're going to say, well, for this third X variable, this is product. It's actually the value of the third thing, of the X star 3, the third thing is the product of previous hospitalization and age. Well, that's 1 times age. That's the value of this made-up X variable. This isn't new data. It's the multiplication of this information. And so we have a third thing, X star 3, that is 1 times age. And then, by the way, here's the comparison person. The unexposed person has a 0. They have age, and they have 0 times age. That's their product of their value of the exposure and age. So this, we want the ratio of the odds of the outcome for these two profiles of people. And so you apply the formula that we used before, beta 1 times e to the beta 1 times the difference in the x's, 1 minus 0. Okay, that's familiar, e to the beta 1. Well, the ages cancel out, because age is the same. So that we have beta 2 times age minus age. But here's where it gets funky. Look at beta 3. So this is just applying our formula. We have beta 3, 1 times age minus 0 times age. Why is that? Well, it's this thing minus this thing, which is just the formula again. And what happens is 0 times age, okay, this piece goes away. And what you get is e to the beta 1 plus beta 3 times age. This is the odds ratio now when you have an interaction model. So what does that mean? That's weird, because it's a variable that itself can change. This is not a single, there's not one odds ratio anymore. What it means is the odds ratio itself changes with the values of age. So at 35, let's say at age 35, this is the expression for the odds ratio. E to the beta 1 plus 35 times beta 3. And when someone is aged 60, let's say, it's e to the beta 1 plus 60 times beta 3. Okay, so there is no one answer anymore. It's now complicated. And that makes sense when you think about, like, what does it exactly mean to have effect modification or interaction? It means that the odds ratio, the measure of association, is changing across the values of the other variable. The effect of previous hospitalization is modified by age. It's changing according to age, and there's no one answer anymore. It's a 35-year-old has a different answer than a 60-year-old. So this captures, in a sense, like when we think about, in stratified analysis, when we thought about effect modification, remember we were comparing odds ratios in two different tables and saying, are they the same, are they different? And we split things apart and compared different heterogeneous answers. Well, the way you do that in logistic regression is through things like this, where you have an expression that gives you a different odds ratio according to different values of this other extraneous factor. So imagine if you had a stratified analysis and you had a 35-year-olds table and a 60-year-olds table, you would get two different answers. Well, this is how you get the two different answers in logistic regression. It's using these product terms. So so now there's no longer one answer. So it's complicated. I always fix this, and it always shows up weird on this monitor. So those are supposed to be betas. So here's a more complicated model. Here's one that considers a lot of interaction terms. And this looks kind of scary, except when you use the e to the beta formula that we use that just has the difference of the x's. And this model is a model that considers previous hospitalization, which we had to abbreviate here, age, sex, PAMU. These are supposed to be betas, the question marks. And by the way, we now have three more terms that considers the interaction of the exposure with each of age, sex, and PAMU. Previous hospitalization times age, times sex, and times PAMU. Okay, so this is a different model. It may be a terrible model, maybe too many terms. And we'll talk about how to figure out whether it's the right model. Well, what's the odds ratio now for the exposure? How do you compare exposed and unexposed with a really complicated model? Well, this is how you do it. You line up all your x's again. You have 7 terms in your model, really, 7x terms. And you say, okay, well, exposed, unexposed, that's still true. We're going to make this comparison. Age is the same, sex is the same, PAMU, and so forth. But here, 1 times age, 1 times sex, 1 times PAMU. That's the exposure, this pH, previous hospitalization, times age, times sex, and so forth. And these are 0 times age, 0 times sex. So these are all 0. These are going to all become 0 in the comparison person because they're unexposed. And we do our same formula of e to the beta 1 times the difference. Okay, 1 minus 0, that's going to be a 1. This is going to be age minus age, that goes away, and so forth. And this is going to be 1 times age minus 0 times age. And so this is going to be, when you have 1 times age minus 0 times age, this is a 0, this is just age. This is going to be 1 times sex, that's just sex, minus 0 times sex, that's going to be just beta 6 times sex. So the whole thing simplifies to just this. So I don't know if you're seeing there's a pattern, actually. When you do the odds ratio, when there's an interaction model, all of the terms that are not multiplied by the exposure go away. So age by itself, sex by itself, PAMU by itself, those have all disappeared. And what's left are the terms that only involve the exposure. So exposure times age, 1 times age times 0 minus 0 times age became this. So this is now a single expression that depends on age, sex, and PAMU values to be kind of specified by you, and then it will give you different odds ratios depending on what you've put in. So you're now your work is not done. It's not just e to the beta. You now need to say, okay, great. I'm going to talk about a 35-year-old male PA with no exposure, no PAMU set to no previous antimicrobial use, and that's going to give me one answer. Now I've got a female who's 17, who's whatever. I get a different answer. And again, that might seem like a headache. Like, hey, that sounds like a lot of work. I just want an answer. But because if in this model we're assuming interaction, we're assuming that the exposure that there's interaction with the exposure, that its effect is changing. And so if we think that its effect is changing, in order to get an answer, we're going to have to specify values for age, sex, and PAMU. So it gets more complicated when there's interaction. The story is not so simple. How do people feel about this? Okay? Questions? I think by now we've seen this 3 times-ish in the last 6 months. I know there was like a summer thing in the middle. But so it's important, and so that's why we're here again. And if you have questions, please ask questions. Okay. So what does this look like in SAS land? So here is the preceding model with the 3 interaction terms with previous hospitalization. Here's what it would look like if you did proc logistic model, MRSA equals all of these terms on the right. You would write all of these on the right side of the equal sign. You write previous hospitalization age. You'd put this in, pre-hosp times age. And lo and behold, SAS is going to give you a table like this. And these are the estimates of all the beta coefficients. And so you would say, based on the formula we had above, that the odds ratio is e to the beta 1 plus beta 5 age, beta 6x, beta 7 PAMU. You would look in your table and say, okay, great. This is the beta 1. This is the coefficient associated with hospitalization. Here's the coefficient associated with that interaction term with age and so forth. And you'd plug it in here. And now, this is your magic formula to start churning out odds ratio estimates. So here's like 3, what you might say, it's I have a 35-year-old who's male, who's been, has previous antimicrobial use. Okay, you put it through the machine, you plug in the values, and then you get 8.1, 3.3, 6.96. That's what we're talking about here. Now, because we have continuous age, you can basically make an infinite number of odds ratios. So you have to kind of, if everything's like binary variables, there's only, if this was age high, low, 1, 0, there would only be 8 combinations, and this would be easy. You'd have a contained set of things to report. In the situation where we have interactions with continuous variables, you're going to have to, choose representative or meaningful numbers according to your situation. So that I don't know what your situation is. But you're going to have to, it could be quartiles, it could be the mean, it can be whatever makes sense at like key representative points to show the odds ratio at. So that's what you're going to have to do here. Otherwise, you're going to have an infinite number of solutions depending on what age you put in. So I'm going to leave that up to you. So I basically kind of suggested this earlier that, when we looked when we looked at our interaction models, we had an interaction model with previous hospitalization times age earlier only. And then we just had this model on the previous slides where we had interaction with age, sex, and PAMU. We saw that there's some kind of pattern here. Right? We have e to the beta 1, the beta 1, the coefficient associated with the exposure, plus all of the coefficients associated with the interaction term times the thing that was not the exposure. So age, sex, PAMU, the thing that was multiplying the exposure. So what we see here is that this is the pattern that will happen when you have a single 0-1 exposure, like a binary, previously hospitalized, did they get the treatment, did they live next to the power plant, those kind of binary exposures. That is going to, the odds ratio in this case is going to always be e to the beta 1 plus the sum of the betas times the control variables, age, sex, these other control variables that we're talking about. So this is a special case of the formula we saw earlier. I don't want you to have to memorize a million formulas. This is actually just a special situation where we have only interaction terms with the exposure, and the exposure is a 0-1, which is a common situation. This is not just some special thing. This is a common situation where you have a dichotomous exposure and you're controlling for other stuff. This is what that expression looks like. E to the beta 1 plus the sum of the betas associated with the interaction terms times these other extraneous variables. And everything in between goes away. The beta 2 through 4 in this last model, which was these terms, those all go away because it's age minus age, sex minus sex, all that fun stuff. So those go away and we have a single thing. Okay, so this is another pattern to kind of see. And again, this is exactly all the same general formula, but distilled for a specific situation. We have these interaction terms with a binary exposure. So I just want to zoom out. I want to point out that there's another slide set online called other scenarios for the odds ratio that you should just take a look at. And it goes through, we just talked about, sorry if this was make you shuffle paper. I'm not going to go through this in great detail. I just want to point you to this slide set to read. And again, I think this is good. This has appeared in lab and appeared some of these situations will appear in homeworks and so forth. What we covered in a sense was, I talked about this general odds ratio formula, but in certain situations, it reduces in interesting ways. So we saw that with a single exposure, with no interaction, you get e to the beta. And the thing we just looked at was a single exposure with effect modifier terms. And that was where we have this special, just jumping ahead to the situation, unless I've already passed it. Sorry. Code, here, interaction terms. This is the situation that we just talked about with interaction terms. So the odds ratios behave in interesting ways. The formula is reduced to interesting things when you have a single exposure coded as binary, a single exposure coded as a continuous variable. What if it's an environmental exposure that has some continuous measurements? What does the odds ratio look like in those situations? What if you have a categorical exposure variable, and so forth? The formula, it's the same odds ratio formula, but it's going to reduce to interesting things. And so we work through all of these in these extra examples. I would just take a look at them, and if you have questions, we can also talk about it more in lab. But just know that it's the same formula just applied to these special situations. Particularly interesting is when you have a categorical exposure variable, when there's not just a single beta 1 times x1, that's your exposure. What if your exposure has 3 levels to it? It's not a yes-no, it's high, medium, low. Well, now it's represented in the model as 2 dummy variables, and the odds ratio is a little funnier. Like, I'll just show you. It's not that funny, I guess. Maybe it's terrifying. So here here's the categorical one. So here's a situation where you have a 4-level exposure variable. Let's say it's where you live. Do you live in the north, south, east, or west? And that's your exposure variable. Well, now, like in this situation, you need to have 3 dummy variables to represent 4 regions of exposure, let's say. Okay, so it's not a simple dichotomous exposure variable. And now the odds ratio is complicated in that there's 3 odds ratios that have a single referent group. These become, like imagine if you coded your dummy variables this way. E1 is 1 if north, 0 other, south, east. The reference group would be west. So we have 3 dummy variables for 4-level exposure. The reference is they're all 0, and that's west. Then the odds ratio that compares north versus west, south versus west, north versus south can be obtained using the same formula, like here. So here we said, what's the odds ratio that compares north versus west? Well, that's comparing a person with 1, 0, 0 versus 0, 0, 0. Okay, that's the 3 levels, that's the 3 values of these individual dummy variables. You treat them just like variables in any old odds ratio expression. And that's e to the beta 1, because this is 1 minus 0, and then 0, 0, and so forth. In the situation where it's south versus west, that's E2 is 1. And so it's 0, 1, 1, 0, 1, 0 versus 0, 0, 0. And then you e to the beta 2. That's the odds ratio for someone that lives in the south. Okay, so this is now more nuanced. There's no single odds ratio. Life is more complicated. And by the way, this model could have controlled for age plus whatever. Okay, so like you could have had other variables here, and they could have all been in this odds where you could have had, my value of age is 57, and my whatever is 3, and right, so you could start specifying in the same old formula all these other control variables, and they might cancel out, they might not, depending on what we're doing and how we're constructing this. But just by the way, the exposure itself has 3 variables to it. So go through these slides, and I think you'll be convinced it's all the same formula, just how we represent our exposures and our factors is going to be tweaked a little bit for these different situations that come up in real life. So that's my little timeout for that. But I want to jump into doing statistical inference with this model. Right now we've just talked about the odds ratio, but there's other questions like, hey, is this odds ratio statistically significant than 1? Or different than 1, sorry. What's the confidence interval around the estimate of my odds ratio? Is it from 1 to 100, or is it from 2.2 to 2.4? So these ideas of statistical inference and understanding the variability in our estimate are important to the conclusions we make. And right, so when we're making inference from our data, there's kind of 3 categories of things that we generally care about. There's the estimate itself, which is the odds ratio, in our case, a hypothesis test, and a confidence interval. Okay, so how do we go about getting these 2 latter pieces out of our logistic regression model? And so, one piece is how do we and by the way, the piece I just glossed over is how we estimate the coefficients themselves. Like, what is SAS doing to actually estimate the coefficients? And then what about the other piece about its variation, the variance, the standard error that we might use to understand significance testing and precision for confidence intervals. There's really 2 pieces to it. How does SAS come up with the beta estimates itself, which is really about this, the point estimate? And then what does it know about the variance of the beta estimates, which is about these 2 pieces? So what's the method that SAS is doing to arrive at the magic answer? Well, in linear regression, there's this thing called least squares, which I think hopefully is familiar. And it was this idea, if you remember from simple linear regression, where you have this like scatter plot, and you're trying to find that like best line that makes its way through all your dots. Okay, what was the best way to make it through all the dots? It was the method of least squares, which minimized the square distance from the dots to this line. It was the magic line at which that sweet spot was found, where basically the distances, or the square distances, were all minimized. Okay, so it was where every dot was at its closest to the line. Okay, so you could use least squares for logistic regression, but no one does it. It's actually not the most statistically efficient method. It will actually give you larger variance estimates than you otherwise could have. So we don't use least squares for logistic regression. Okay, so this is cool for linear, but not for logistic regression. So I'm going to talk about what we're going to do in logistic regression. It's called maximum likelihood estimation. But while we're thinking about linear regression, there were other things that came out of the least squares method that we would really like to have analogs of for logistic regression. Do you remember when in linear regression, you wanted to test whether a single beta coefficient was 0? Because this means whether something significantly contributed to the model. Is this factor significant? Did I have to have this on the model? And there were 2 tests for that. There was the partial F test, and then there was a T test. The partial F test looked at the contribution to the sums of squares of a given factor after you controlled for the other factor. Does that ring a bell? Sums of squares, type 1 sums of squares, type 3. So that's what this was. This is this thing called the partial F test. It was said, like, after I've controlled for a whole bunch of other stuff, have I actually explained more of the sums of squares with this extra factor that I've now controlled for? This was the type 1 sums of squares, let's say, or the type 3, depending on what you're doing. This was an F test. There was another test that was a T test. That was this thing, beta hat over standard error of beta hat. This was a t-test that actually was also able to give you the type 3 sums of squares answer. I don't know if you remember that. There was 2 kind of alternative formulations. We're going to talk about logistic regression analogs of these. The first analog is more or less the likelihood ratio test and then the wall test. Those are going to be what we're going to call them in logistic regression, and they're going to be kind of different. Then there was this other thing called the multiple partial f-test. Remember that one? It's called the chunk test, maybe, in 591. It's just like a totally unappealing name. Its actual name is the multiple partial f-test, which I guess is a mouthful. But this was testing whether a set of any betas are significant or not. It's like, are these 3 things significant? Like, I want to test for a whole bunch of variables at a time. That was called the multiple partial f-test, and it was a generalization where you're testing a bunch of these. And then there was another thing that we did in linear regression, which was the confidence interval for the beta itself, which, if you remember, like kind of manipulates this formula to get a confidence interval around beta hat. And it was beta hat plus or minus a t statistic with a degree of freedom of error. So there was a degree of freedom, and then at 95% confident, or whatever it's going to be, times the standard error of beta. We're going to call this the walled confidence interval in logistic regression. So these are things you did in linear regression, and they're going to all have logistic regression analogs, but a little different. And they're not. This is not going to be an F distribution, for example. It's going to be a chi-square. So in logistic regression, we're going to do this thing called maximum likelihood estimation. You really don't have to do anything differently. You don't have to do this. SAS is going to do this for you, but it's important to have an understanding that it's doing something a little different than least squares. So there's this idea of the likelihood function, and it is the thing that is being maximized. Okay, I know it sounds really silly because I called it maximum likelihood estimation, but this thing called the likelihood function is the joint probability of observing all your data. And I'll explain what that means with an example on the next slide. But basically, it's a function that represents, it's going to look a lot like the logistic model, the 1 over 1 plus e to the minus alpha and so forth. And what it's trying to do is find the set of values for these things that make your data most likely to have occurred. Okay, I'll show you what that means. It's going to iteratively solve a whole bunch of equations to find the maximum. It's going to try to find the maximum value of L, and it's going to say, okay, at that maximum value of L, what did these have to be? Okay, I'll show you again. We'll have a simple example to show you what that means. So it's an iterative process. There's no closed form solution for it. So in least squares, for linear regression, you can actually write kind of algebraic in a happy way how to kind of do it by hand. In many cases for MLE, you kind of need to iteratively solve it on a computer. There's formulas for it, but you need a computer to solve this set of equations. And so, and there's going to be 2 flavors of this, the conditional and the unconditional model. The unconditional model is the standard version of logistic regression and MLE, and that's what we're most of the time using. The conditional model made its appearance last semester when we were doing matched analysis, and it's this, it's a version of the model to use when you have when you would need so many terms in your model relative to the number of outcomes that you'd have too many terms in your model. And this came up in matched analysis. We're going to talk about this. This is a special case model. This is the usual case model, the unconditional model. So what do we mean by maximizing the likelihood? Like, what does that mean? So let's take the simplest like binary data scenario. Okay, so let's take a study that has 100 subjects, and there's 100 subjects, and the disease happens to 75 of them, and 25 of them don't get the disease. Okay, this is the simple, really simple study. Okay, well, using like your biostats 1 hat, you'd say, okay, I think that this kind of feels like a binary. This is a binary process, and the binomial distribution. This is to say binomial. The binomial distribution might dictate whether people get the disease or not. 75 of them did, 25 of them didn't. We want to know what is the imagine if I brought you this data. I have 100 subjects, 75 of them got sick, 25 of them didn't. What's the probability of getting the disease? Okay, you'd say, oh, it's 0.75. Like you would in a knee-jerk way just say, oh yeah, my best guess is 0.75. It doesn't have to be 0.7. It could have been 0.71 and you just saw 75 in your single instance. But your best guess intuitively is 0.75, 75% chance. Well, why is that? The reason is you just did maximum likelihood estimation in your head. Let's say the data were distributed as binomial, not binary, or you could essentially the same, with n and p. Remember, in the binomial distribution has n and p as its two parameters, the number of trials and the probability of the event occurring. We want to know p, right? That's usually what you care about. I bring you some data. Here's some data. What is the probability of the event occurring? That's basically what you always want to know. And the odds ratio and other things are kind of derivative of that. But the basic idea is this p. We want to know p. Well, what you could do is write this out as a probability problem. Here is the binomial distribution. Remember this? Like the number of trials choose the number of successes times p to the number of successes 1 minus p. Is this familiar from the binomial distribution from a year ago? Something like that, last fall. This is the binomial distribution. This dictates the distribution of 100 trials, like imagine coin tosses is always the way this is introduced. 100 coin tosses with a coin that 75% of the time gives you a heads or whatever. This dictates the number of successes and failures that you would see at 100 trials. Okay, so in biostatistics, you were usually given the p, and you had to say what's the probability of all this occurring. You would say like the probability, it's a fair coin, so p is 0.5, and we're going to have 75 heads. What's the probability of seeing 75 heads? That's kind of one direction of thinking about this. That's like the way you would have learned this in biostatistics. Is saying like, given an n and given a p, what's the probability? What we're going to do is kind of play the game in reverse. We're going to say, what is the value of p that makes this quantity the biggest? Okay, the value of p that makes this quantity the largest is actually the maximum likelihood. We're going to call this thing the likelihood. This spits out a probability. If you remember, this is the binomial distribution. This is the probability of observing 75. This is the probability of observing 75 successes. Okay, this is just what it is, the binomial distribution. And we want to say, what is the value of p that makes the probability of seeing 75 successes the biggest? Okay, and you can graph this. And it would be a parabola in this case, or you could use calculus. Take the derivative of this expression with respect to p, and if you did either of those, if this is a single variable calculus problem, take the derivative. What you would get is that the value that maximizes this function, it achieves its peak at 0.75. It is what you will get. You can literally ask the computer to graph this or do calculus. You will get that the best value of here to have the biggest probability is 0.75. Okay, and so what you would have intuited just from eyeballing the data. Okay, but this is going to get a whole lot more complicated when some of the subjects are male and some are female and some are exposed. Some have this, some have that. In this situation, everyone's kind of the same. So we solved for p. We maximized p. So in logistic regression, what's on the left side of the equal sign? P. It's the probability of the outcome, right? It's the probability of y given all the x's. That's what we just did here. This was solving for the probability of y, and there's no x's. But so this is the idea of maximum likelihood. It's finding the optimal value of p. And what happens in logistic regression is that p has a whole lot else going on. P equals 1 over 1 plus e to the minus alpha, beta, and so forth. So it gives more to figure out. But the idea is that you're finding the values that maximize the value of L, the likelihood. So, by the way, this was exactly the same. If I had a data set with 100 rows in it, 100 rows, 100 observations, 75 got disease, 25 didn't, and I fit a logistic model to it, I can actually get this. because this is equivalent to a logistic regression model with only an intercept. There's no covariates. There's just people. 75 of them got the disease and 25 of them didn't. And this is exactly, we just did logistic regression with an intercept-only model. And if you fit that data set with 100 people, you would get that the intercept is 1.0986 alpha is this. And what you would get is P of what? P, this thing that we did before, 1 over 1 plus e to the minus 1.0986, this, is equal to 0.75. Okay, so maybe it's a little circular. I kind of said it's going to be 0.75, and here it is, it's 0.75. But what SAS is doing is it's finding the values of the terms in your model that it is finding the terms for alpha here, let's say, that give you the maximum value of p, which is 0.75. So we anecdotally, or kind of looking through this with calculus, said it has to be 0.75. SAS is saying, I need to find a value of alpha that equals 0.75. And we're going to have betas, and we're going to have all these betas, and this is going to get more complicated. But the idea is it's maximizing the probability of your data. So it's really hard to develop like an intuition around MLE. So this is a very simple example. But basically, it can add more terms and find the pieces that make your data most likely. On board? Yeah. All right, well, feel free to ask questions or send emails or bug your TAs if this still doesn't make sense. But this is the general idea. SAS is solving for these alphas and betas. Okay, so given that this is all going on, okay, that it's trying to find the values that make your data most likely, that are most likely given your data, there's another thing there's an interesting finding that comes up here, which is, let's say you have 3 models that you have this data set, 200 people, they're in Grady Hospital, and you're going to fit 3 models to it. One controls for, has just an x1 and an x2 in it, and the other one adds a third term, an x3, and this one even has more terms, x1, x3, and so forth. They're all fit on the same exact data. Well, it turns out that the likelihood for the smallest model is always less than the likelihood for the model that has more in it. And similarly, this model has a higher likelihood than the ones below. And the idea here is that the probability, this quantity, the likelihood is increasing the more it's fitting your data better the more you add to the model. This came up in linear regression. Do you remember all subsets regression, model selection? Remember that? All subsets, model selection. And you looked for a change in the R squared. And the idea there was that, like, hey, the more I control for in the model, the more I'm going to explain. That came up. Like, it just maybe you get a very tiny incremental advantage. Like, I controlled for 61 terms instead of 60, and I really didn't need that 61st term. And I tested that. That's this in the MLE. There's no R squared because this is not least squares. R squared, it was a linear regression least squares thing. The logistic version is the likelihood. We're going to look for whether the addition of a term meaningfully increases the likelihood, is the idea. Just like we were looking for meaningful changes in R squared. Yes, it's going to always go up, but the question is whether it goes up by such a fractional amount. We explained nothing new. The model fits no better once we added 16 more terms. That's the idea. So this is exactly what we were doing in linear regression with the R squared and the all subsets approach. So the likelihood goes up. It just may not be, maybe a very tiny incremental change. And so we're going to use this idea for hypothesis testing. So the likelihood ratio test is a test that is going to be like that R squared test that exploits this relationship that for a given set of data, the likelihood is the smaller models have lower likelihoods than the bigger models. And we're going to look at the likelihood changes when these other things are in the model or not. So we're going to say, like, hey, I have this model, and then I drop these 2 terms. Did the likelihood change? Is going to be what we're doing. And this is exactly the R squared tests in linear regression. And by the way, that's also the same as the partial F test. It was just called, in linear regression, it's all called different things. So what we're going to do to make a hypothesis test around the statistical significance of a variable in the model, whether it's contributing at all in your logistic regression model, is we're going to make this test called the likelihood ratio test. And it's going to, the null hypothesis is that for some number of beta terms, let's say we're going to test one at a time, or we can test 5 terms in one chunk. The null hypothesis is that the betas are 0, okay? Which means that e to the betas are 1, right? So either way, they're not important. If their e to the beta is their odds ratio is 1, they don't change your odds, or the beta is 0, they have no contribution in the model. That's the null hypothesis. And what we're going to do is compare the likelihood of a model with and without the variables of interest. And that is going to be a test of whether the likelihood changes. And so the thing that summarizes the difference between the two models is this thing which is -2 times the log of the likelihood of the reduced model over the full model. Okay, this is the quantity. This is the analog of what we did in the chunk test with the mean squared error effect. The mean square, the change in the mean square of one x given the other x's over the mean squared error. That was the linear regression version. There was no -2 log. But in linear regression, it's the same idea. You made this ratio. And here, it's -2 times the log of this thing, the likelihood of the reduced or the likelihood of the full model, which you can rewrite because of the way logs work and fractions work. You can say -2 times the log of the reduced minus -2 times the log of the full model. So you can write this in either format. It turns out SAS gives you quantities only as the -2 log likelihood. It doesn't give you just the likelihood, it gives you this thing. So when we compute this test, we're going to actually use this one, this format of the formula. And basically, SAS is going to give you this quantity once, and you're going to get it again, and you're going to subtract the two. So this is what comes out. This thing is distributed chi-square with the number of degrees of freedom associated with m, which is the number of things that you were considering to be dropped, in a sense, in the model, or the ones that are hypothesized to be equal to 0. So what that means, if I'm saying like, hey, are these two terms significant? That's is beta 6 and beta 7, are they statistically significant in the model? That's going to be a chi-square with 2 degrees of freedom because I'm dropping 2 terms. If I'm dropping a single categorical variable with 2 dummy variables, that's also 2 terms. It's the number of variables being dropped, not the number, like if it's a 3-level high, medium, low, and there's 2 dummy variables that get dropped as part of that, in the statistical test, it's a 2-degree of freedom test. Okay, so here, here's a situation where I want to know, is beta 3, let's say I have this model with 3 terms, is beta 3 statistically, do I have evidence that it's statistically different than 0 or not? To test this, I'm going to look at the -2 log likelihood in this full model with beta 3, and I'm going to compare it to a model that removes it. And I'm going to run a second proc logistic command on this model, and I'm going to compare its likelihood. I'm going to get a different -2 log likelihood. I'm going to compare them, and that's a chi-square 1 test under the null hypothesis that this is 0. Okay, so that's the idea. We're going to run. You have to run actually proc logistic twice. Here's a situation where we have 2 variables that we're considering to drop, beta 4 and beta 5. This is to say 4 and 5. Let's change that. Okay. Oh no. Sorry. Okay. So. Okay, so beta 4 and beta 5, we're going to consider dropping both of them, and then it's a 2-degree of freedom test is the basic idea. Okay, so we're going to, whoa, that was odd. Okay, so we're going to have a full and a reduced model, and we're going to compare the -2 log likelihoods. Okay, that is the likelihood ratio test, and we would do this in SAS by looking at the output for the likelihood twice. We're going to run 2 models. Okay, there's this other thing called the walled test, is another way to do the just to do a statistical test, a hypothesis test for the significance of a beta term. And it's simpler. It's the beta hat over the standard error of beta hat. You can write this as a normal statistic or as a chi-square 1 degree of freedom if you square this thing, which I'm showing down here. This is given to you in the output in SAS. You get the estimate and then the standard error of the estimate in your table, your standard SAS table for logistic regression. This quantity should be normally distributed. And so a z-test of this quantity will tell you whether this term is statistically significant or not. Or you can square this, and it's a chi-square with 1 degree of freedom. I think Logistic actually gives you this version, the chi-square test. So this is different than the likelihood ratio test. It can be done inside of a single model. You don't have to compare a full and a reduced model. And this is a different test. With a different, it's a different test. What's cool about this is you can actually compare it to other null hypotheses, not just equals 0. You can compare it to equals 2 and equals 3, and we can talk about that. You basically subtract another value in here. This is very similar to t-tests and other tests that came up in previous courses. This is the same formulation, that you have a quantity over the standard error of itself. So these generally, both approaches more or less will give you the same answers. The likelihood ratio test is a slightly more powerful test. It will always give you pretty much a slightly smaller p-value, let's say. And when you have small sample sizes, that will get the gap between them will get exaggerated in some sense. Like if you have a very small sample, then likelihood ratio test will be more powerful. It's easier to do a wall test though, because it only requires knowing beta and its standard error. And so generally, the likelihood ratio test is the preferred methodology. It's the more powerful test. But in practice, actually, the wall test is easier because it's there on the screen right in front of you in your standard output. And by the way, this walled quantity, this thing, beta hat over the standard error of itself, can be used to make the confidence interval around a given beta estimate. So let's say you want to know the confidence interval around beta 3 hat, which we actually don't really care about that much. We actually more care about the confidence interval around e to the beta hat, which is the odds ratio. But that's what I'm saying down here. So you can use these quantities you can use this quantity of the standard error and a cut point for the z distribution, like 1.96, which I'm sure you've seen 100 times. You can use this expression to come up with the confidence interval around beta hat, but more importantly, e to all of this is the confidence interval for the odds ratio, if the odds ratio is e to the beta 3 hat. And we've already seen today that the odds ratios can get a bit more complicated, so we'll have to talk about that. But in the simple case of an e to the beta 3, or an e to the beta 1, knowing its standard error, the standard error of beta hat 1, you could come up with the confidence interval for it. So again, this can get more complicated if this is not a 0, 1 variable. If there's other variables in your odds ratio expression, this is going to get a little more complicated, potentially. So what happens when we have interaction? And what if actually life was complicated and this was your model, model 3, which we saw a model 3 above, and I wanted the odds ratio for x3, which I forgot what that even was. That might have been age or it was either age or sex. And I wanted let's say it was sex, I wanted the odds ratio for x3. Well, there's interaction terms with product terms with x3 here. And if you applied the formula from earlier, the odds ratio for x3 involves all of these terms now. So now what's the confidence interval for this? This is actually more complicated because it's the odds ratio. This thing is this whole exponent. You need the standard error or the variance. Here I wrote it as the square root of the variance, which is the same as the standard error. But you need to know the standard error of this whole thing, which is not in the standard output of SAS. That is not going to tell you what the standard error of beta 3 plus x1 times beta. It's not going to do that for you. So this is a little more complicated. This is because you need to know the whole standard error, the whole the square root of the variance. Sorry, I wrote it in this variance way. So this is more complicated because it's not a single standard error. This is a complicated thing. And it's going to be, we're going to, in the next slide set, we're going to go into some examples of doing this in SAS. This is going to be a special request from SAS. You're not going to want to do this manually. And you're going to use the estimate or the contrast statements to get this. So this is just like a cheat sheet that shows you kind of how what you did in linear regression stacks up to what we're going to do in logistic regression. Likelihood ratio versus partial F's and the Z and the T and all that fun stuff. So that is one slide set. And we're just going to start the other one because we have like 5 minutes and I got to make up for time here. So without totally confusing everyone. So this is we're going to exit just kind of intro to logistic regression and just start thinking about how this how we could use this model to think about epi questions. And this is going to be less do people have these slides? Yeah? Okay, thank you. I'm trying to put these up at least 2 or 3 days before every lecture so people can have them available. So I just want to throw this out for a minute, and obviously we're not going to get more than a few slides in, but you can use the machinery of logistic regression in a highly targeted way to answer epi questions. And the way that we're going to do that is by rewriting the model yet a little differently than just betas and x's. We're going to use a different nomenclature to actually reflect the things we care about as epidemiologists. And this new nomenclature, which is actually not that new because this was introduced by Dr. K at the end now of 534, so this is going to be your second time seeing it, so it's not going to be so new anymore. But this nomenclature is going to be a more relevant way of thinking about the model and how to arrive at the best model. And so the EVW model is basically a way of organizing the predictors of the regression model into things that are useful for us. The idea here is that not every variable is the same in your model. Not every x is the same, and we shouldn't necessarily call them all the same thing. Because x's can be exposures, they could be control variables, which might be confounders or effect modifiers, and by the way, also mediators, which we're not going to gloss on as that much. But those are kind of other ways that variables exist in your world. Like imagine you made a DAG, which I'm sure after Dr. Howard's class, you're in love with DAGs now, and you made this DAG that represents your life. You know, you're a research problem, right? You've got exposures and you've got confounders and you have some disease outcomes, and it's really complicated. In this DAG, this directed acyclic graph for the people that haven't taken EPI 591U, in this representation, this model for what your research problem is, variables are not all x's and there's not just one outcome. Sometimes it's an exposure, sometimes some variables are these other things, confounders. Effect modifiers don't work so well in DAGs. But we want a model that actually reflects our epi problem. Okay? And so we're going to use these letters. E and C represent kind of primary variables that we went out and measured. And then V and W are how these control variables function in the model. Sometimes they function as confounders, and sometimes they're effect modifiers. Right? A variable can actually appear as both things. It can be both a confounder and an effect modifier, which is kind of mind-blowing. But these are the things we go out in the world and collect. We collect exposure and control variables, and then in the model, the control variables can do any of these two things. So here's our example again, this MRSA example. So in a simple model, like this simple model, here I'm actually showing the output. This was just the simple 2x2 result of previous hospitalization and the outcome of a resistant infection. Here, I'm not going to write exposure. I'm going to write X. I'm not going to write an X variable. I'm going to write E for exposure. Okay, so this is what we call an EVW model with just previous hospitalization and nothing else to it. Here's this other model that we just saw in the last slide set. Here we have an exposure variable still, previous hospitalization, and 3 control variables, age, sex, and PAMU. Notice I'm not writing age, sex, and PAMU. I'm just writing C2, C3, C4, but they're not X variables is what's important. There's not, now we have the model is cataloging my variables in 2 ways. Exposure, control variables, okay? So we're not just doing this to introduce more letters. There's a reason for this, and it's going to be about how the odds ratio expressions work out. And it's going to make life hopefully a bit easier in the long run. So here I rewrote an earlier model, but with E's and C's. And we're going to say that this is an EVW model that has this kind of situation. It's got an exposure, previous hospitalization, and 3 control variables, age, sex, and PAMU, that are being used as confounder control variables. And so I'm going to also call them V1, V2, and V3. You're going to say, well, why the hell did you have V's and C's being the same thing? That's really annoying. And the reason is that C's are going to also appear as part of effect modifying terms. A V, which so Dr. K, 30-something years ago, actually published this system of doing analysis. And I actually don't know why he called it V, because it doesn't sound like confounder. But it means confounder. And so they're functioning, these control variables, this control variable 1 is functioning in a confounding control role in the model. Okay, it's not functioning in an effect modifying role in the model. Compare that to this other thing we saw, and this is probably where we'll end, I guess. This model we also showed in the last slide set, but with all X's and whatnot. This was a model where each of these C variables, age, sex, and PAMU, was involved in an interaction term with the exposure. Okay, so here it was PAMU times age times sex. I mean, sorry, not PAMU. Previous hospitalization times age times sex, and then times PAMU. That was these 3. We can rewrite it as an EC, EC1, EC2, EC3. Okay? So here, C1, age, is used twice. It's used twice, once as in consideration of confounding control, and then a second time as an effect modifier term. And I say effect modifier because it modifies, as we talked about before with these interaction terms, it's modifying the effect of the exposure. In the odds ratio expression for the exposure, the odds ratio itself was modified. It changed according to the value of age. That's by definition what an effect modifier is. I put in a different age, and lo and behold, the odds ratio changes, modified, changes. Anyway, so this, if I rewrote the model this way, you would say, aha, exposure, confounder terms, and then exposure times these kind of control terms. These are effect modifiers. So a way to kind of index what's going on in the model is you say this is an EVW model. We have an exposure that's previous hospitalization. 3 C variables appear in this confounding situation over here. And by the way, they also appear as effect modifier terms. Okay, so the model has 3 components, E's, V's, and W's, and some things happen in age and sex and PAMU appear in both places. So this is going to be really important, and it's going to we'll continue it more later on Thursday. Thank you. And by the way, Jeb sent out an email about labs. So for people in Patricia's lab, she's still out, and you will follow the instructions about going to the appropriate room, be it 1000 or the other room. Thank you.